Okay, so this is a talk about the evolution of Robocode strategy. So Robocode is a programming game where you control a tank. That tank can move around, it can fire, you can turn your turrets. All those things can be done independently. Um, so here we see two different sample bots, and they're having a battle here. So let's look at the code for this blue guy. So he just moves back and forth, and then when he rotates his turret at the end of each motion, and he will shoot at the enemy when he sees them. So here's the code for that. He just moves ahead 100, turns his gun, moves back 100, turns his gun, and then we've got this on-scanned robot event, and we'll just fire whenever we scan a robot. So, this is a really basic robot. It only performs one action at a time. For more advanced robots, you can both, turn your gun, fire. You can perform all of these actions simultaneously. So that's the kind of robot that people will generally be writing. Okay, so here's the rules for the game. We don't actually care about the rules, so I'm just going to ignore the rules. So there's two rules that actually matter. One of them is that bullets can't be seen by your robot, so you don't know where the enemy's bullets are. The other one is that bullets are slow, so they're faster than robots, but not very much faster, which means that if you move properly, you can dodge them, unlike real tanks and real bullets. Okay, so let's talk about some basic strategy. So here's here's a robot. We're going to fire at this other robot. So we're just going to linearly project out their motion, assume that they continue at their current velocity, and we'll aim at the intersection of our bullet and their tank. So based on our bullet speed and their robot speed, we're going to make this triangle and aim at that corner of it. Slightly more advanced one, we're going to assume that they keep the same angular velocity, so they're going to travel in the same arc that they're currently traveling in, and we're going to aim at the point on that arc, again, where our bullet will intersect based on their speed and our bullet speed. Okay, so some really basic motion. We just want to turn perpendicular to the enemy, and we're just going to move back and forth. So this will make it, so that we are hard to hit, right? There's a large possible number of angles that we could be at by the time their bullet gets to us. And if they just linearly project out our motion, then we're going to stop and turn around, before the bullet gets here. Okay, so let's take this to the next level. So we're going to keep track of multiple movement strategies. And so we'll have different patterns that we can move in. We could just oscillate, we'll move in a circle, or we'll just ram the enemy. And then we'll keep track of how many times we've won or lost a round using each of those. And then we'll pick, whichever one is the most effective against the current enemy. So if they're using something simple like, the linear projection, then maybe oscillating is a good idea. If they're using the arc projection, then using the circle is probably, circular motion is a terrible idea. So we'll just keep track of that and we'll use the best one. So a slightly more complicated aiming idea, we're going to record all of their motion, and this will form, a history of moves that they've made, and we're going to find, look at the past, say 10 moves that they made, and find something in their history that matches that, and then play forward their motion after that. So we'll do some pattern matching, and then we'll assume that they're going to follow the same motion, and we'll aim at the intersection of our bullet and where their pattern says that they're going to end up. So any sort of bot that moves in a regular pattern, like a circle or oscillation or anything like that, we will likely be able to predict where they're going to be by doing this. Okay, so let's take it to the next level. So next level targeting. So let's look at all the possible angles they could be at. We'll consider 0 to be, if they stay in place, and then 1 will be the biggest possible angle that they could get to if they, continued forward motion or moved forward at the maximum speed. The -1 will be if they moved backwards as fast as possible. So they have to be somewhere in between, -1 and 1. So what we're going to do is when we fire a bullet, we're actually going to fire a bunch of virtual bullets, right? And so these are, we're going to track which of these virtual bullets hit them. So we'll fire, maybe one at -1, one at -0.9, et cetera, et cetera. And we'll track which one hits them. So in this case, we got the bullet at 0.7 hit them. So we're going to keep a histogram that says the hit rates for each of these bullets. So these virtual bullets that we fire. And then when we're going to aim, we'll just aim at the peak, aim at the whichever bar is highest in this histogram, because that's the place that they're most likely to be. So the next level of movement is to sort of assume that the other guy is doing this. They're building up a histogram. So we want to move randomly within this reachable area, but we want to make sure that we select points to move to, such that the histogram is as flat as possible. So you can sort of do random movement, but tune the way that you do that random movement in order to make sure your histogram is as flat as possible. Okay, so what's the next level? So the next level, we've got this histogram idea, and what we want to do is we want to segment this data. So we're going to keep multiple histograms based on the current situation. So in this case, I've done distance on one axis and acceleration on the other. Obviously there's a lot more things you could segment the data on, but we'll just do those two, and we'll say, okay, here's what the histogram looks like in each of those. So when we go to fire at them, we'll say, okay, currently they're at mid-range and constant speed, so we'll use that histogram to pick the angle to fire at. So the next level of motion. So we can detect when they fire. So they're at 100 energy. We see that energy drop to 98. So we assume that they fired a bullet. We know how fast that bullet is going to be traveling. So we can model this incoming bullet as a wave. So this wave is, all of the possible angles that they could have fired at. And what we're going to do is we're going to apply the histogram from their perspective, and we're going to say, okay, on this wave, here's the points that the bullet is likely to be at, here's the points that the bullet is not likely to be at. And we're going to travel to whichever point the bullet is unlikely to be at. So in this case, I've color-coded them, so we're going to travel to the blue area because we think that's pretty safe. We're pretty sure that they fired at the red area. And we'll track these histograms from their perspective, and keep them updated all the time. So based on our recent motion, we'll basically ensure that our recent motion, our future motion, does not match our recent motion. So this is a recording of two robots. This one is drawing onto the battlefield using a debug graphics feature. So you can see these are the incoming waves of bullets. The one that's drawing them is actually the bottom one. So the pink dots that it's drawing out are its choices for moving forward versus backwards, and then the incoming waves say how likely a bullet is at each of the locations. Okay, so let's take it to the next level. So we've got these histograms. They're segmented based on various ways of looking at their current situation. So in this case, speed and distance, or acceleration and distance. But the problem with this is that we may have a lot of different segments, and so therefore we've got a lot of different histograms. So any given histogram accumulates data really slowly, so it may not have enough data to be useful. Also, we might be segmenting on dimensions that are not useful against the current robot, which just dilutes our data. So how do we kind of mitigate these problems? So what we can do is we can use multiple segmentations. So we've got one unsegmented histogram at the top, and then we've got a slightly segmented one in the middle, and then we've got a highly segmented one in the bottom. So when we go to fire at the enemy, we're going to pick the histogram from each of these that matches the current situation. We're just going to add those all up. Maybe we'll apply some weights, and we're going to come up with an overall histogram, and then we'll use that to pick our angle to fire at. And we'll also do a similar thing for modeling incoming bullets from the enemy. We'll use a similar way of using multiple segmentations to build our histogram. So another way that we can completely avoid the problem of these histograms being too segmented is we can just insert these waves into like a n-dimensional space. So in this case, there's 3 dimensions: how long they've been traveling at the current speed, what their heading is, how far away they are. But you could extend this out with many more dimensions. And then when we go to fire, we're going to pick all of the points, all the k points closest to their current situation. And each of those points represents a wave in the past. And each of those points also stores what was the correct angle to shoot at. So maybe we'll pick 100 points that are closest to their current situation, and we'll build a histogram on the fly. And then we can say, okay, what was the best angle, based on the historical points that are most similar to the current situation, what was the best angle? And this has the nice property that we can just say, pick the 100 points closest to the current situation, and we will always get enough data. So at the very beginning of the round, when there isn't much data, we will be picking points that are pretty dissimilar to the current situation. And then as more and more data accumulates, we'll pick ones that are closer and closer to their current situation as more and more points get inserted into this space. Okay, so final level here. So we've got, when we fire, we've got this incoming wave of potential bullets from the enemy. But bullets can actually intersect other bullets. So when we fire, we can look at this as creating a shadow. There's a certain part of that incoming wave where we know for sure that there can't be a bullet, because if there was a bullet there, then it would have intersected our bullet. So therefore, we've got this known safe zone, and we can stay, as long as we stay in these shadows, we can't possibly be hit. So here's what that looks like. So the robot on the top here is going to be, it's tracking its incoming waves and drawing them onto the battlefield. So these green points are points where it knows there can't be a bullet, because if there was a bullet there, it would have been intercepted. So you'll see it tries to stay in low probability regions, but if it can reach one of these known 0 probability regions, then it will move to those instead. Okay, so that's the history of Robocode 1v1 strategy so far. I hope you enjoyed this talk. Feel free to ask me any questions about Robocode. There's obviously a lot of complexity that I've skimmed over. But I spent a long time doing this. I enjoyed it quite a bit, and I love talking about it. So that's it. I hope you enjoyed the talk.